Welcome back to Physics Fundamentals. In this video, I want to talk about physical quantities, which is a more in-depth topic than the title may suggest. But the basic ideas here all come down to measurement. And measurement in and of itself is more general than you might think of at first glance. To measure something means to observe it and write down some characteristic of it. So, for example, I might take the pen that I'm writing with, observe it, and say that this pen is black, and it has some silver highlights. That is a measurement of the pen. It measured the color of the pen. Measuring color is certainly a thing we can do, but usually not what we really want to do. Usually, in this course, we're going to be looking for things that we can measure numerically. That's what this idea of quantities comes to. A physical quantity is a numerical measurement that you can take of something that exists in the world. Measurements that you are familiar with might include things like length, weight, and time. Now, in order to measure things, you need some sort of a reference, right? To get a numerical value, you need to have some meaning of what those numbers mean. And that's where units of measure come up. I'm going to assume that coming into this course, you are most familiar with the US customary system of measure, where lengths are measured in things like inches, feet, or miles. Weights are measured in things like pounds and ounces. And time is measured in hours, minutes, and seconds. That's certainly not the only system of measure that exists, and it's probably not even the most useful to us, but it's a good place to start because it's the one I assume you are most familiar with. Let's take a look at just feet for a moment. What is 1 foot? Well, in the earliest time of measure, a foot was literally a person's foot, right? A person looked at an object and said, that's about the size of my foot, and used that as a way of communicating to others in the community. Then we got a little bit more sophisticated, right? That's about 2/3 the size of my foot. That's about 3 times as long as my foot. And we could start talking about these measurements numerically. Of course, that starts to raise some issues because different people have different sized feet, right? I am about 6 foot tall, a little bit over. My foot, by coincidence, happens to be just about 1 foot long. My wife is a head shorter than I am. Her foot is only about 9 inches long. And that could cause a pretty significant discrepancy, right? If I say that something is about 5 of my feet, and my wife says that something is about 5 of her feet, we're going to get very different looking things out of that. And so early humans had to try to find a way around this problem. One of my favorite approaches is the unit of the rod, which is now more or less defunct. It's not officially part of the US customary system anymore. But 1 rod is 16 feet in length, and it's defined as the distance traveled by 16 men of the village standing heel to toe. So you get a bunch of people to line up, you put their feet one after the other, probably staggered, so half of them put their left foot in, half of them put their right foot in, and they don't have to trip on each other in order to get all these things together. You cut that thing in half, cut the result in half again, and 2 more times. And now you have a geometric way of averaging the feet of everyone in the village to get a unit of a foot. Another standard that was attempted that didn't really work all that well was, well, maybe the local lord, the ruler of the area, will be the standard, and that person's foot is what we mean by a foot. Right? Well, first of all, that's great for business. Now I can start a business of cutting pieces of wood to the size of the ruler's foot and selling ruler feet to the people of the village. But that's also problematic because, well, what happens when the ruler changes? What happens if the ruler passes away and his daughter takes over? Right. So another standard is the yard. 1 yard is 3 feet in length. And I say that this is a standard because it is a physical object. A device was commissioned, and it still exists. It's held in the Royal Society of London's vaults in a climate-controlled space. It is made of solid gold. It is exactly 1 yard long, and its cross-section is a square that measures exactly 1 inch by 1 inch. And for quite some time, that was the standard of the yard. It was the only thing in the world that was exactly 1 yard long, and we could compare all of our other measurements to that. In the time since then, we've come up with some more sophisticated ways of measuring things. Currently, a yard is actually defined based on the SI unit, the metric unit of a meter, and a meter itself is defined based on the distance that light will travel in the time it takes for a certain atom to undergo a certain phase transition. So we have transitioned from physical artifacts to more general objects. Another way that we have transitioned is to make things a little bit more expanded, right? We have this unit of the foot. And so we realized, well, if we have objects that measure, say, 4 feet in one direction and 6 feet in another direction, well, you can define the area of that object as the product of the length and the width. 4 times 6 is 24. And if you multiply feet times feet, you get square feet, which in the US customary system is almost always written as SQFT. For our purposes in this course, we're always going to write it as feet raised to the second power, right? Second power is square. Likewise, we can have a cube. Let's see if I can draw a cube today. That's a reasonably good approximation of a box or a cube or something. And maybe this measures 4 feet by 3 feet by, say, 2 feet. And then the volume of the box, the stuff contained in the box, we can multiply 3 times 4 times 2, and by coincidence, numerically, we still get 24. But if we have feet times feet times feet, we have now cubic feet, which in the US customary system is always written as CUFT. For our purposes, we're going to write it as feet to the third power. All right. So it takes a lot in order to have a system of measure. And these sorts of ideas, these sorts of relationships have just developed over time, and things got very messy. Right? If you look at the imperial system of measure, which is what the US customary system is based on, but was originated in England, there's actually something like 20 units of length. There's a good 45 units of volume, which is just not that useful. And so the system of measure that we're going to spend the most time with is the SI system, which sometimes you'll see referred to as the metric system. There are subtle distinctions between the SI system and the metric system. They are both French systems. The metric system was created as part of the French Revolution. The revolutionaries saw that creating a new system of measure and adopting it in their nation was a great way of showing the progress of their society from the corrupt royal society to the society of the people that was more modern at the time. The SI system is the International Scientific System, except it's in French, so they say it backwards and they call it SI instead. And there's a lot of overlap between them. The SI and the metric system both use the meter as the unit of length. The SI system uses the kilogram as the unit of mass. The metric system uses the gram. The SI system uses the second as the unit of time. The metric system uses the hour, but acknowledges the minute and the second. All right, so relatively similar between them. And we can use that to our advantage. Let me get my head out of the way. It's time to start doing some calculations, although these calculations should be fairly straightforward. One of the nice things about the metric system is the use of SI prefixes. There are a ton of these. I don't need you to know all of them. Quite honestly, I don't know all of them. But you should be familiar with kilo, which means times 1,000. You should be familiar with centi, which means divided by 100. Milli, which means divided by 1,000. And micro, which means divided by 1,000,000. The symbol for kilo is K. The symbol for centi is C. The symbol for milli is a lowercase m. Lowercase is important here. There is also a capital M for mega. I'm not going to get into it because I've never actually seen it used. But then we've already run out of M's. And so the symbol for micro is the Greek letter mu, which I always thought looked like a U until somebody recently showed me that it's actually supposed to be a script letter M. Right. But when I write it, it tends to look more like a U, so I don't know. With the SI prefixes, we get immediately the information we need in order to have conversions. So if I want to write 1.63 kilometers in meters, well, kilo means times 1,000. So this is 1.63 times 1,000 meters. 1.63 times 1,000 is 1,630. Going in the other direction can be a little bit tricky. All right, so if I have, say, 0.075 meters, and I want to write that in centimeters, well, I know that centimeter means divided by 100 meters. And so I have to work backwards. And remember, that's going to mean times 100 and get 7.5 centimeters. That's a lot of logic to keep in your head. And for that reason, along with several others, I tend to find it useful to start writing things out. So if I want to convert 0.075 meters, well, I can always take anything and divide by 1 without changing it. Now I'm going to multiply this by something involving centimeters. And if a centimeter means divide by 100 meters, then if I have 100 centimeters, that's the same thing as 1 meter. 100 centimeters and 1 meter are the same measurement. And if you take something and divide by itself, you get 1. And if you take something and multiply by 1, it doesn't change anything. But by carefully constructing how I am doing this, I have meters in the numerator and meters in the denominator that are going to cancel each other out. And I can see pretty clearly that I want to take 0.075 and multiply by 100, and when I do, the units are going to be centimeters. 0.075 times 100 is 7.5. This notation, which is called the unit factor notation, becomes even more useful if we start looking at those compound units. Right? If I have 750 square centimeters, and I want to write that in square meters, well, I can take 750, put it over 1, that doesn't change anything, and I know still that 1 meter is the same thing as 100 centimeters. So I know I want to arrange it in this order. But this factor of centimeters will only cancel out one of the two factors of centimeters in 750 square centimeters. To cancel out the other factor, I'm going to need to multiply again. Another 1 meter over 100 centimeters. This second factor of centimeters will cancel out the rest of the centimeters there. And I have 750 divided by 100 times 100. And then my units are going to be meters times meters, which is square meters. All right, 750 divided by 100 is 7.5. 7.5 divided by 100 is 0.075. Right? 750 square centimeters is 0.075 square meters. All right. There's several other things that I could do in this video, but I think there's only one more that I think is really important to talk about right now, and that's liquid volume. Right? We've talked about you could take lengths, multiply themselves to get solid volumes. Liquid volumes traditionally have had different sets of measurements. And the reason for that is that liquids are very important in culinary applications, and so using a system of measure based on things that you have in a kitchen. Right? In the US customary system, we had the cup and the pint as units of liquid volume. Literally, that was somebody's teacup and a beer stein were the references used for those. But for that reason, traditionally in the metric system, we have a unit of liquid volume as well. It's actually a really convenient one because the liter is defined so that 1 milliliter is the same thing as 1 cubic centimeter. And so immediately we have a conversion between solid volume and liquid volume. It could be more convenient, but even at this is pretty convenient. So if I have, say, 2 liters, a standard sized soda bottle sold in the United States, and I want to write that in cubic centimeters. Well, I know I can always take anything and put it over 1 without changing it. I know that there are 1,000 milliliters in 1 liter, and that will cancel out the liters here. And I know that there is 1 cubic centimeter in 1 milliliter, and that will cancel out the milliliters here. So we are left with 20 times 1,000, and the units left are cubic centimeters. So 20,000 cubic centimeters. If I wanted cubic meters instead, I could convert further. I don't, because cubic meters are actually pretty huge compared to liters, and that gives me a really ugly number. But some of that also gives you why the liter and the milliliter can be so useful, right? 2 liters is a very standard amount of liquid for culinary applications. Trying to express that in cubic centimeters, it's 20,000, which is a ludicrously large number. If you wanted to do cubic meters instead, it would be 0.0002. I think I said the right number of zeros. But those numbers just aren't very useful to work with. And so for that reason, having this liter as a measure of liquid volume for culinary applications was very important in the metric system. It kind of trickles its way into the SI system every now and then, but we do our best to avoid it. All right, with that, I think I have run out of things to talk about, so I will wrap up here. Thank you as always for joining me. I'll see you next time.